In this section I will talk about modulation. What is it and why do we need it? Well, think of what do we have in computer science? We're talking about zeros and ones. So all we have are digital values, zeros and ones. So 0 and 1. Not that much, but well, this is what our digital world is made of. So the first step is the translation of this digital data into an analog signal, so-called baseband signal. So we will learn, we can use different means there, but for example, we do some so-called analog shift keying. So 0 could be a certain sine wave, a very weak one, and 1 could be a strong one. We could even think of on-off or something like this. Okay, so that's a very simple way of modulation. There are many differences of how you translate this digital data into the analog signal. I will give some examples. They all have some differences in how efficient they are, how robust they are. What does robustness mean? Well, think of interference. If, for example, there is some electrical engine close by, some interference, then the interference adds to the signal and could create a signal like this. So now at the receiver side, is this a 1? And this is also 1? So we'll have some transmission errors. Okay, so some of the schemes are more robust, some are not that robust. So that's one of the ideas. Okay, so first this type of modulation, or we learn different type of modulation, let's say a lower frequency and a higher frequency. That's the first step. That's the first step, digital modulation. And then we have to do a second step. That's called the second step, is our typically an analog modulation scheme. Yes, I know we can do everything digital with software defined radios, but these are classical steps. Because then think of our classical radio station example, analog radio station. We have the moderator, we have music, and all this happens more or less on the same frequency band. So music, that's up to something between 30-40 Hertz and up to 16,000 or 20,000 Hertz, something like this. But the problem now is all the different radio stations now have the same baseband frequencies, but as we learned, we want to do something called frequency division multiplexing. So now we have to shift this frequency, we see this frequency up to a certain carrier frequency. So the carrier frequency is, for example, for the radio station we had this 88.6 megahertz. So a very, 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 very high frequency. And the idea now is that we use our baseband to modulate this carrier frequency. So for one type of modulation, for example, we could have a bit higher frequency around the carrier and a bit lower frequency around the carrier. And this helps us to separate the different, in this case, analog radio stations. One reason for this analog modulation is our FDM. There are other reasons. Think of you want to transmit your voice over fiber optics or over microwave link. That means you cannot use an arbitrary carrier frequency. For fiber optics you have to use something in the range of infrared light or visible light. So 1500 nanometers, something like this, 850 nanometers, whatever. Or for microwave links, you have to use something like 60 gigahertz, for example. So depending on your medium, you have to adapt the frequencies you use. That means shifting your baseband to a certain carrier that fits to the medium you use. And then we learned something about antennas. Antennas, for example, are lambda fourth or half the wavelength, depending on the type of the antenna. So basebands, think of, okay, baseband is around, let's say, 10 kilohertz, for example. Well, 10 kilohertz wavelengths are huge. So we cannot have kilometer long antenna, maybe submarines, but not for your cellular phone. Okay, so there are several reasons for shifting the baseband after this digital modulation with the help of analog modulation to a so-called carrier frequency. There are three basic schemes. We can modulate the amplitude, that means the strength of the signal. We can modulate the frequency and the phase. Amplitude, frequency, phase. Remember the parameters of our sine wave some sections ago. So what are the steps? Again, modulation. You take your digital data in, you perform a digital modulation, you create a so-called analog baseband signal. Then you use the radio carrier. Our example is 88.6 megahertz. And you use the baseband signal to modulate the radio carrier. And then you transmit this over the antenna. On the receiver side, you receive the signal over the air. You have to know the radio carrier. That means you tune into a certain station. That's exactly what you do at your classical radio. You tune into a station. That means you adapt the radio carrier. And this allows for the analog demodulation. You create the analog baseband signal. And then based on this baseband signal, which is not at all an ideal, super nice signal, but with a lot of interference, whatever, you have to synchronize. So where are my bits? Where do they start? Where do they end? We will learn some technologies for that. And then you have to decide. Decision, that means 1 or 0. And then you create your digital data, which might or might not be the same as the data you had on the sender side. If it's not the same, you can use forward error correction. That means you insert redundancy to recalculate the original data. Or you say, oh, I didn't understand, please repeat. So you can do something that's called ARQ, automatic repeat requests. So you perform retransmission. So FEC, ARQ are the typical mechanisms to, well, fight against the errors that interference created. So the first step is digital data into our analog baseband signal. This first step is called the digital modulation. And we typically use a modulation that is also known as shift keying. And then this digital modulation is known as amplitude shift keying, frequency and phase shift keying, ASK, FSK and PSK. ASK is a very simple scheme. So basically you say, for example, there is a signal, a nice sine wave, if we have a 1, and there's nothing for a 0, and for a 1 we again see something. But what happens if we have interference? So interference, that means you add some interference up here, for example. So this could look like a 1, and then suddenly you make a 1 out of this 0. So amplitude shift keying, yes, feasible, but usually used in combination with other schemes. We can do something that's called frequency shift keying. We translate our bits into different frequencies. Maybe you remember those old modems, fax machines. You heard these nice beeps of different frequencies over the classical analog line. This was a classical frequency shift keying, so we had different audible frequencies for ones and for zeros. We even had different frequencies for the directions, so we could do something that's called a full duplex, sending and receiving at the same time. So 1 in this example has a higher frequency, 0 has a lower frequency. So that's the idea. If we now have some interference added, well, the hope is you can still distinguish this lower and higher frequency plus interference. And then we can do something that's called phase shift keying. It's a bit more complex, but it's quite robust against interference. Phase shift keying implies a phase shift. That means you have your nice sine wave, and then suddenly you do a phase shift, or in this case a rotation by 180 degrees or pi. So you shift your sine wave suddenly. This sudden shift is not so nice for technical systems, but that's here just for explanation. And technical systems can easily detect this shift in the phase. We as humans cannot detect this if someone shifts the phase in an audio signal, but machines can easily detect this. So these are the 3 basic ways of translating digital data into analog signals with their pros and cons. So usually you combine the schemes. And just to give you one example, I show you a bit more advanced frequency shift keying used in the classical 2nd generation cellular phone system GSM. So there, and I will explain this using the diagram, there basically you do a certain pre-computation to avoid this sudden phase shift. Remember the example on the last slide? I had this phase shift, this jump here. Well, technical systems don't like this because, you had this sudden change and sudden in no time doesn't work in real systems. And you have to adapt as technical system, creating some not so nice frequencies. So we want to avoid this. So we want to do some kind of a minimum in this kind of, jumping in the phase. So that's the idea. And then we apply certain filtering, but this is for computer science. So I will not go into the details here. Just if you want to look this up, it's quite often referenced as GMSK, Gaussian Minimum Shift Keying. That's used in GSM. Just to show you the basic idea how this classical, many years old, started in the early 90s, this 30-year-old system, how this system does the first steps of digital modulation. Okay, example. First of all, we have our raw data. Raw data, that means our ones and our zeros. So what the system does is, internally, it doubles the even and the odd bits. So let's assume that's the first bit here, second bit, third bit, just for the example. Then we use this bit and we double it. So basically double all the bits, and then we know we have 2 frequencies, one low frequency and a high frequency, which is exactly double the low frequency. So that's double frequency. And then we have a table here on the right hand side with a very simple mapping. We simply look at a certain point in time. Let's look at the third bit in our example. Third bit. What happens with our even bits and odd bits at this third bit? The even bit is low. That's from the second bit. So even bit is low and the odd bit is high. So even bit low, odd bit high. That's exactly the case for our bit number 3. Even bit low, odd bit high. And then the table tells us, okay, we take the low frequency, in this case low frequency, not the high frequency, low frequency, and we take the original signal, not inverted. This results here in this part of our signal. Yes, this is all simplified, but that's the basic idea. So now the system, using this MSK scheme, goes through all the bits, doubles them, uses the table, and then creates this so-called MSK signal. And no matter what combination of bit you have, you will see, we will never have this jumping of the phase. We will switch between low and high frequency, yes, but you see here, never this jump in the phase. And that's quite important, and this creates nice signals. So that's one of the basic ideas. So this is then our analog signal, analog baseband. This is still baseband, our analog baseband signal, and basically we take this signal and then we shift it up to the certain carrier frequency. The carrier frequencies for GSM in this example I will talk a bit later in chapter 4. So that's one way of doing this. There are many more modulation schemes, shift keying schemes. A classical phase shift keying scheme is BPSK, binary phase shift keying, quite often used in classical satellite systems. It's a very robust scheme, not that efficient, but very simple. So basically, now look, we show this as constellation diagrams. So you have a sine wave for the 0, and if you want to transmit the 1, you use the inverted sine wave. So that's the basic idea. Yes, then we have these phase shifts, etc. But this is so simple, it works. But as you see, for each of these symbols you transmit, so a part of the sine wave, we can only transmit a single bit. We could code also more bits into one of the symbols. The next example, called QPSK, we can code 2 bits per symbol. So 2 bits per symbol. So you see, now 1 is basically a sine wave of a certain amplitude. That's the length of the vector here. And a certain angle, certain phase shift. So the new symbol determines the shift of the sine wave. That's the idea. And it's a bit more complex, but it needs less bandwidth compared to the classical BPSK. And you can now combine this scheme with other schemes, and you can also have relative phase shifts, etc., etc. If you're interested in this, DQPSK is one example used in the personal handyphone system IS 136. So also classical second generation systems. So that's the basic idea, and remember those 2 figures are basically the same, just one is in the time domain, the other is this constellation diagram. Now, why coding only 2 bits into a symbol? Why not coding 4 bits into the symbol? Yes, okay. So there are many schemes called Quadrature, Amplitude Modulation, QAM. And those schemes, they combine amplitude and phase modulation. So code n bits into a symbol. Great, why not? The example here shows you a 16 QAM, so you have 4 bits in a symbol. And this represents basically a certain magnitude of the amplitude, so how strong is the signal, and a certain angle. So that's the idea. So if you look at the symbol 0011, so 4 bits coded into this, and 0001, it's the same phase but different amplitude, or you find other examples with different phase and same amplitude. So here we code 16 different symbols into this constellation diagram. So 4 bits per symbol. So we could go to 5 bits, to 10 bits, to have 1024 or whatever points in the constellation diagram. Yes, we can do more and more, but I will explain this but on the next slide. This gives you an example of the modulation used in the digital video broadcasting system for terrestrial broadcasting. DVB knows the DVB-T for terrestrial, DVB-C for cable TV, and DVB-S for satellite. So the current version is DVB-T2 for the terrestrial transmission. And there you see, we have here 64 QAM, and the new DVB-T2 uses 256 QAM. So many points you code here. Okay, great. So that means we can transmit more and more bits per second. Yes, in theory, yes. So if there's not that much interference, you can distinguish all the different points on the receiver side. Because what happens on the receiver side? Think of the sender wants to transmit, let's say, this point here in the upper right corner quadrant. So you want to transmit this, that's on the sender side. On the receiver side, depending on the interference, you may receive for this single transmitted point, well, it might be here. This is rather a point cloud around this point in the original constellation diagram. So if you have this as the real point, you mean you could receive something around this. Now the next original point might be here, and again point cloud, depending on the interference around this. What happens if there's a lot of interference and suddenly you have a situation like this? How do you separate them? You basically draw a line here and you say, okay, all the points above the line, they belong to this symbol, and below the line they belong to this symbol. So that's one of the problems. Okay, what do you do if the point is somewhere here, exactly in the middle? But what happens if you pack more and more points into this constellation diagram? That means you have also points here and here. And all the other points are the points you receive. So signals you receive. It will be harder and harder to actually recreate the original symbol based on this cloud of points. The more interference you have, the harder it will be to detect the original symbol. And that's the problem. If the points are further away from each other, it makes life easier. Remember BPSK, only 2 points. Only 2 points in space. 2 points. Classical satellite transmission. Then you can have a lot of interference, but it's still possible to say if it's left or right, in this case of the y-axis, so of the Q branch. So the point here is, with good reception, the DVB-T system may be able to resolve the entire constellation. But if reception is poor, maybe you can only say, I receive something here, or there, or there, or there. But you don't know if this really belongs to one of these points, these symbols, in the 64-QAM constellation. So, but at least you can say, okay, it's here, upper right, upper left, lower right. But this is basically a QPSK scheme. Four gray regions. So at least, no matter if it rains or snows, you will be able to receive at least this kind of upper right, lower right, this QPSK. That means in perfect reception, 64-QAM, under poor reception, at least QPSK. So, and now DVB uses a simple trick. You code high priority data into those 2 bits. The two bits that at least tell you lower left, lower right, upper left, upper right part of my constellation. And low priority, remaining 4 bits. If the conditions are nice, well, for example, you will be able to see a more fine-grained picture. If transmission conditions are not that good, at least you will see a frame each, let's say, each second or whatever, depending on the scheme. So, under good conditions, you can watch the soccer game and you see the ball. Under bad conditions, well, you see at least, there's the green lawn and maybe something like this, but you maybe may not be able to follow the ball, for example. But at least you will see some pictures, but not a high frame rate, for example. Or you could code the picture in high priority, but the color in low priority, then you could receive something in black and white. Or if you know how MPEG works, you can code the different I, B and P frames with different priorities, for example. So whatever, by the B frames with lower priority, something like this. So different ways of coding hierarchical modulation. Okay, some questions. Think back of modulation. Why do we need these 2 basic steps? In real systems we have some more, but these 2 basic steps. So why can't we just use the digital modulation in today's schemes? So what do we do with the digital modulation? What are the typical schemes? And now back to this question. How can we decide, if we look at these diagrams and these points we receive, how can we decide which pattern was originally sent when this point lies somewhere between other points? So now think of coding more and more. That means packing more and more bits into a phase shift. So more and more points in the constellation diagram. Why is it quite difficult? And you saw an example how to react in case of higher and lower interference, and how does this actually influence the data rate. And you should have a basic understanding of this, because this is exactly what we use, for example, in LTE to adapt to different transmission conditions. So under better conditions, higher data rate based on a different modulation scheme. If the transmission is, well, problematic, a lot of interference, bad weather, whatever, lower data rate using a more robust modulation. So we can easily adapt the modulation scheme. That means the robustness of the transmission.